Hello, guys. So in this recording, we're gonna, go over a very important and very, basic devices that we're gonna use, from now on in this course, which is basically the flip-flop. Okay. So and the first type and the most important and most famous type is what's called the D flip-flop. Okay. So we see the D latch in the previous recording. And the latch is basically a device that latches the input whenever it change. And this D latch has a very important an advantage, which is there is no forbidden states. So the D flip flop is a D latch, but this this latching, we can say, happens only when there is an edge, either positive edge or negative edge. I mean, there is a clock like this. Look at, here is a clock here. I mean, here is an extra input, we can say, and this extra input has a signal like this. How we generate this is not your problem. This is not our course. Okay, we're gonna assume all the time that we have this and it's available. Okay, so the latching will happen at the positive or negative edge of the clock. For example, if there is one here, I mean, if the during the clock was 0, for example, this is a positive edge. If D changed at that point in time, for example, and the output here was 0, it will not change. It will not latch this one, this new input, basically, until that particular moment when the clock changes from 0 to 1. At that point, that will change from 0 to 1. It will latch the input, basically. Whatever it is, if it's 0, it will be 0. If it's 1, it will be 1. But only at the positive edge. One may say, if the input changes within the pulse in which the clock is 1, I mean, it becomes 0 again here at that point. So this becomes 0 now. This will keep 1 until that point in time when the next edge arrives. At that point, that will be 0, and so on. Whatever the input is, it will be reflected or copied to the output only at the positive edge. Same for that guy, the negative edge one. But the behavior that I just explained will happen when the clock goes from 1 to 0. At this particular moment, 1 going from negative edge 1 to 0, or this particular moment. Okay, that's basically, how the D flip-flop will work. And basically, all the types of flip-flops that we're gonna study in the next video. They all work, or I mean, the output will change, we can say, basically at the clock edge, either positive or negative, based on the design. So there are many implementations or ways to implement this D flip-flop. Okay, here is an example. The first one is called master-slave D flip-flop, which is a very good one, easy one, and really easy to understand. It's basically a hierarchical, or structural, design from the D latch that we studied so far. So we're gonna bring two D latches, the D latches that we studied the last video or last recording, and put one here and one here. Okay, forget about this master-slave stuff, just the D latch for now. Let's now assume a value for the D and check when it's gonna appear on the output queue here. Okay, but we should remember something in the beginning. You remember, guys, this is not a normal D latch. This is the latch that we studied at the end of the last recording, that has an enable input. And we said that when the enable is 1, 0, I'm sorry, this was memory. the output will keep its value regardless of the input change or not. Then when the enable is equal to 1, it will latch. The output latches or copies, you know, whatever on the input. Or latches the input, whatever it is. 0, 1. If the input is 0, you know, the output will be 0. If the input is 1, the output will be 1. Good. So let's do it. Let's do it. Let's assume, for example, that the clock now is 0. We are here, for example. And at that moment, D become 1. It was 0 in the beginning, it become 1. Okay? So, clock is 0. Let's check at that particular moment. The moment at which D become 1. Clock is 0. So, 0 is going to the enable. So, this first latch, which is called master latch, okay, has enabled 0. Enable 0, so it's a memory. So that will not change. No change. Let's assume there was unknown value. Let's call it a Y, for example, like the example here. At the same time, the clock is going to an inverter here. So this inverter will give us 1 here. So the second one, the second latch, which is called the slave latch, has enabled 1. Enable 1 means it will latch whatever on the input. So we're going to see Y here. So whenever the clock is 0, we're going to see Y on the output here. Y is just a known value, whatever it is. Call it X, call it Y, you know. Now let's check what's going to happen at that particular edge when the clock changes from 0 to 1. So let's do it with another color. So now the clock is 1. So the enable here for the first D latch is 1 now. So the output of this first D latch, the master latch, will latch or copy what was in the input. So the input here is 1, so it will be copied here. And Y become 1, the output will become 1. At the same time, the clock is going to an inverter, so this will be 0. So the enable is 0, okay? So since the enable is 0, the second D latch, the slave D latch, will not copy what's in its input. Remember, the input of the second latch is connected to the output of the first latch. They are the same wire. But now we have 1, the value of the D, on the input of the second latch. But still its value, its output is Y, still. So it looks like this flip-flop is not positive edge, because if it was a positive edge, we know that at the positive edge, the output should take or latch the input. But it didn't. It kept what it have right now, which is Y. Y is again is any value, 0, 1, whatever. Okay. Let's check now. Of course, this will continue whenever the clock is 1. Now let's check what will happen when the clock goes from 1 to 0 again. So let's, you know, have another color, green now. So 0 now. So 0, so the first one, the first latch has a 0 now. It has a 0, so it will be disabled, or memory, not disabled, memory. Memory, that means the output will not change, so it will stay 1. And again, the clock is going to have some inverter here, so this 0 will become 1. So this enable of the second latch is become now, it is now 1. The latch has enabled 1. That means it will latch the output of this D latch will latch or copy what was on its input. On its input right now, there is 1. So there will be 1 here. Look what happened. The value of the D copied to the output Q at the negative edge. That's why it's a negative edge triggered D flip-flop. This is called D flip-flop. D flip-flop. The output will only copy the value of the input, or take the value of the input, or show the value of the input, which is D, at the negative edge. Of course, I did here the example, or assuming D is 1. You can do it 0. You can assume it even D, generally, you will find the same. Okay? That was basically the master-slave D flip-flop negative edge. That particular configuration is negative edge. What if you want to convert this circuit into a positive edge D flip-flop? What you're gonna do? Actually, it's a very small tweak, very small, tiny one. We will not add anything new. We'll just change, the location of some component here in this circuit. So I'm gonna give you, 30 seconds to answer it. So you can just pause the video and, think about it for 30 seconds or something. So I hope you get it. So we're gonna move the inverter from that branch to that branch. That will convert this circuit from a negative edge flip-flop to a positive edge flip-flop. Let's check. Let's have the same example. Again, D change it at that point and become 1 or 0, whatever you like. The important stuff here is that when the positive edge come, I should see 1 here or 0, according to your example, whatever you choose. So the clock now at that particular moment in which D become 1 is 0. So we have 0 here. So that guy will have 1. And we're gonna go, of course, there is no inverter now here. It's just a short circuit wire. So we have here 0. So that guy is disabled. I mean, it will the output of this D latch, the slave D latch, will keep its previous value, whatever it is. Let's call it X. Its previous value is X, whatever it is. Just an unknown value. The first one has enable equal to 1. So it will latch. So the output will latch the input. So this Y will become 1. That's good. This will continue until we reach that point. At that point, the clock changes from 0 to 1. Let's check what will happen with another color. So we have here a positive edge. So that become 1. 1 goes through the inverter, so the enable of the first latch will be 0. So the output will not change. It will stay 1. Memory. That particular case here. And now we have 1 on the enable of the slave latch. And that means this latch will latch. So the output will latch the input. And look, the 1 appears on the Q on the positive half cycle, just with a very small tweak. Which is better, negative edge trigger or positive edge? That depends on the application. Sometimes you find this, sometimes you find this. Okay, that's good. That's basically one design of the D flip-flop. Another design is this big one here. Okay, it's a little bit tricky, but it's really nice. So let's do it together. So let's start also with red. Okay, this guy now is positive edge triggered. So we are expecting to see D on the Q here, whatever D is, 1 or 0, when the positive edge arrive. Okay? So let's assume 0 first. So if you have 0 on the clock here, this NAND and this NAND has now one input is 0. So 0 NANDed with any other input, with anything, will give you basically 1. So we have 1 here. And also 1 for the second one. 0 NANDed with anything will give you 1. And you know, this particular, this is basically a latch. If you guys remember from our last video, this is just SR, the S prime R prime latch, right? So this S prime R prime latch, when it has 1 1, it will be memory. So the output will not change. So that means no change here. The Q will remain Q, the Q bar will remain Q bar. If it was 1 and 0, it will remain 1 and 0. If it was 0 and 1, it will remain 0 and 1. Okay, let's check the other outputs of the other NAND gates at that particular moment when we have a clock 0. So now we have 1 here. So 1 NANDed with D, 1 and D is D, D NANDed or inverted will give you D bar. This D bar will go here. It will have no change on that particular output. It will stay 1 because one of the input is 0. But it will also propagate through that wire here that I'm highlighting to the very top NAND gate. So we have here D bar. And this input is 1 because it's coming from that particular output, the second output is the second NAND gate output. So 1 NAND D bar. 1 and D bar is D bar. D bar inverted, it will give you D. So with 0, we have the following outputs of the 4 NAND gates. D, 1, 1, D bar. Now let's check what will happen when the clock changes from 0 to 1. So let's do this with another color. So this becomes 1 now. So this one is going to that NAND gate and also that NAND gate. Okay. So with that one here, this NAND gate that I'm highlighting, it has one of the input 1, 1 and D bar. So D bar and 1 will give you D bar. Take the inverter. This will be D. How about this one? The second one, it has one input D from the previous value of the clock when it was 0. This one here. And the second input is 1. D NAND 1 is D bar. Let's check the other outputs. The first, the topmost NAND gate and the bottommost NAND gate. So now this is D. D NANDed with D. D and D is D. Take the inverter, D bar. No change. Good. And look now to the topmost NAND gate. It has one input, which comes from the bottom, still D bar. But this one now become D bar. D bar, NAND D bar. D bar and D bar is D bar. Take the inverter, it will be D. No change as well. So these are the 4 outputs when the clock changes from 0 to 1. And it's a function of D. I mean, D can be 0, can be 1, whatever it is. Now what we care about is the second, the output latch, this latch in here. This is, as I said, S prime, R prime latch. Okay? This latch in particular, when the set is 0, the output will be 1. When the set is 1, it's inverted. The output will be 0. Let's check this. So this particular S bar R bar latch now has S equal to D bar and D, R is equal to D. Let's put values and see. Let's put D equal to 1, for example. That means S is equal to 0 and R is equal to 1. So Q, we know that when S is equal to 0 and R is equal to 1, you can review the last lecture, Q will be 1 and Q bar will be 0. And look, Q is equal to 1 just like the D. Very nice. Now let's assume D is 0. What's going to happen? So if D is 0, so S will be 1 and R will be 0. When S is 1 and R is 0 for that particular S prime, R prime latch, Q will be 0 and the Q bar will be 1. Look, Q is equal to D. Both are zeros. So that's basically a D flip-flop. Positive edge D flip-flop. Why? Because this happens at the positive edge when the clock changes from 0 to 1. Okay. And you can also, and here is, before we continue, here is a function table of the D flip-flop. Okay. And that means positive edge. When the positive edge comes and D is 0, Q will be 0 and the Q bar will be 1. When the positive edge comes, D is 1, Q1, Q bar is 0. That's as simple as that. You can even design the same circuit with what's called reset input. So the reset input, which is that input in here, okay? This is basically, like the enable, again, like, the decoder and the multiplexer combinational circuits that we studied before. But it's really important. It's actually very extremely important for such particular circuits. Remember, this circuit has a kind of feedback. I mean, the output is connected to the input somehow. Okay, and sometimes it's really hard to simulate from the practical issue now. It's a practical issue now. It's hard to simulate, and we're gonna see in model sim that without a reset input, we're gonna have errors in the output, and the simulation might not even run. Okay, that's because the future output is dependent on the current output, and the current output is unknown. For example, at the beginning of the simulation, we don't know that there is no output, basically. There was no input. Okay, and that might cause a problem. But with the reset input, you can reset the circuit to some value so you can start simulating. And we're going to do this a lot. And without it, as we will see in the VHDL lessons, we're going to see that the model sim might not simulate your circuit and give you errors. Okay, because it can't determine the value of the outputs. Because the value of the output depends on the value of the output, the previous output, of course. And at the beginning of simulations, there was no output. So how can he, do the simulation for you? That's why we need most of the time this reset input. And the reset meaning is the following. When the reset is 1, for example, force the output to some particular value. For example, make the Q equal to 0. You can do it as inverted logic as well. I mean, when the reset is 0, make the Q is 0. But the idea is the same. Whenever you reset, whether this reset is 1 or 0, you are gonna have in the output, you are gonna force the output to some particular value. Whatever the clock, whatever the inputs, you will have this value all the time as soon as there is a reset. You assert the reset input. So for example here, this is an inverted logic reset. When the reset is 0, whatever the clock, whatever D, X means don't care, whatever they are, Q will be 0 and the Q bar will be 1. Can we design it in an opposite way? Yes, you can. You can design it that when the reset is 1, Q will be 0 and you will force Q to be 0, and of course Q bar should be 1 because they are complement. And then when the reset is 1, the circuit will do its function. It will be D flip-flop. Most of edge D flip-flop. Okay? Let's check that. So if we put 0 here, we should see 0, 1 all the time. Let's check that. So if we put 0, here will be 0. So 0 on that NAND gate, 0 NANDed with anything will give you 1. That's basically the second output here. So now you should just see 0 in the queue. That will be the end of it. So now we have this as 1. So let's check. The reset is also going to that. So we have here 0. So this guy will be 1. So this guy will be 1 as well. The reset is also going to this. So this will, yeah. So S now is 1 because of this second NAND gate. Look now, this NAND gate has 1 and 1. 1 NAND 1. 1 and 1 is 1. Take the inverter, it will be 0. Look, exactly what we are expecting. Then, when the reset become 1, look, these inputs is 1 to NAND gates, so they will not affect the NAND gate. I mean, the output of the NAND gate that has a reset input will be determined based on other inputs. Okay, guys, that was basically the D flip-flop. In the next recording, we're gonna explore other types of flip-flops. Okay, then we're gonna take the VHDL lessons. Thank you very much for watching this video and see you in the next video. Bye-bye.